And I want to argue in terms of the bias-variance decomposition of the mean squared error. So the mean squared error would be the expectation of an estimated parameter minus, let me write a theta for the true parameter, and I'm taking this squared, and the expectation here is with respect to the sampling distribution. So if I get one training set or another training set. And I can rewrite this by subtracting and adding a constant. So I've subtracted and added the same thing. So I've done nothing to my equation yet. And now I can decompose this. So I can say this is, let's say this is part A, and this is part B. So I will get a squared plus b squared plus 2ab. This is a squared. And then we have b squared. And then we have the mixed term, and the mixed term is going to cancel. Bless you. Okay, and it's going to cancel because you see we can take this here out of the expectation operator. So essentially, this thing here is going to be 0, and then the whole thing is going to be 0. And now these terms have names. The first one is the variance, and the second one here is the squared bias. And you see this was the true parameter, and once I've taken the expectation, this is already constant, so I can omit this outer expectation parameter. So I can also say that the bias is okay. I can omit this expectation, and if I'm not talking about the squared bias but just the bias, I'm omitting the squaring, and then this is what I find. Okay, and I'm because these are important, I'm going to splash out a frame here. So what do these equations mean in words? The variance tells us how big is our expected square deviation of a particular parameter estimate for a particular training set from the expected parameter that we find when averaging over all training sets. Whereas here we have our systematic fitting error. So how far does our average estimate deviate from the true estimate? And if you remember the picture when we talked about the capacity of a classifier, I can draw something similar here. I can plot the bias, which goes down as we increase the capacity. I can plot the variance. So this is the bias. This is the variance. In our example here, the sum of the two, or the, let's say here, squared bias. The sum of the two would be the mean squared error. And least squares regression is, if the linear model is true, has zero bias. So we are here, especially if we fit few points in high dimensions, we have zero bias, but we have quite a large variance. So we're somewhere in this regime here. And this is why it can make sense to introduce some bias, but in that way reduce the variance to get an overall decreased mean squared error. Okay, so this is what we obtain when we start to regularize. So the mean squared error can be lowered by regularization. If the variance reduction is larger than the increase in the squared bias. And the normal least squares has zero bias. But remember the variance, which I'm writing down here again. The variance can be very large if we have correlated observations. So our aim should be to try and reduce the variance. And one way to do so is to use ridge regression. So, hold on, Bernhard. I'm trying to think how to best explain this. Yeah, my last blue screen also took away the last picture I had painted for you. Okay, I'll do that after the break. So, what I what I can say qualitatively is the following. In this space of parameters, yeah. Okay. So instead of capacity, last time I just wrote flexibility, and capacity has a well-defined technical meaning in the statistical learning theory that Wapnick and colleagues have developed, whereas flexibility is a vague term. And this time I tried to avoid flexibility because we're talking about, you know, least squares regression, so we're just fitting planes anyway. But I did not want to give the technical definition of capacity now. If you remember the function counting theorem, it said that in high dimensions we can partition a data set in practically every possible way if we have few enough points in sufficiently high dimensions in general position. And the flip side of this is that we can fit practically every cloud of points with a plane, given that we have sufficiently high dimensionality. However, and this is what this formula is telling us here, is that our estimate is not going to be very reliable. And the estimate not being reliable means that perhaps we have some true value beta 0, which we don't know. What we actually found from our data set was a beta hat. And if I am now assuming the if I now assume Gaussianity of my errors, then I can draw this posterior distribution here. And I have handcrafted this example in two ways. One way is that if you look at the difference of beta 0 and beta hat, is that they mainly differ along the first axis of my parabola, because this covariance that I find for my estimate here tells me that if I'm wrong, I'm probably wrong somewhere in this main direction of the parabola. And I've handcrafted in a second way. My picture here suggests that the actual values for beta hat are larger than the true values that I find. So I want to argue that if we now restrict ourselves to, if you remember in the support vector machine, we somehow shrunk the space of possible models, and we can do the same here by saying that I want to put an upper L2 or L1 norm on my coefficients. And I want to, for the ridge regression, this is the L2 norm. And I now want to find the minimum of my, or I want to find the most probable parameter value subject to this constraint here. And in this particular example, subject to these constraints, the minima would lie along a line here. So this is a way of shrinking, and that has become a standard term in this field. This is a way of shrinking my original estimates. Okay, so I want to introduce a bias towards making my estimates smaller. And if you look again at this picture here, this is just what I did. I introduced a bias that said, okay, I want a solution that on the one hand fits my observations well, But on the other hand, I want the regression coefficients to be relatively small. And then depending on how strong I made this bias, by setting it to values 1 or 10 or 20, I obtained these solutions which are actually pretty close to the true figure which is shown here. Okay, considering that we have noisy measurements, it's not perfect, but it's close. Okay, now I think enough intuition. Let's look at the math. So what ridge regression does is it minimizes the following. So the sum of squared errors as before, plus a user-defined term times the L2 norm of my regression coefficients. So what I'm doing is I'm adding up these two potentials. So if you think of this as a potential, assuming normality of my errors, this is going to be a Gaussian distribution, or if I take the logarithm of it, this is here a parabolic, a quadratic potential, and this is also a quadratic potential, and I'm now summing up these two potentials. And you know, if you sum up two parabolas, you get a new parabola. But if I introduce more and more of this one, so if I make lambda and lambda the regularization parameter, if I make lambda larger, I'm going to shift the center of my resulting parabola ever closer to 0. So the first part is just what we saw in normal least squares. And now with this additional term here, this gives you ridge regression. Now you can take the derivative of this with respect to beta. And so all of these squared L2 norms we obtain by multiplying those vectors with their transpose, so taking the inner product with their transpose, and then I obtain let's take away the 1/2 and okay. So I can solve this for beta, and I find this is XX transpose plus a little bit of the identity matrix to the power of -1. So you see that, well, the least squares case results for lambda equals 0, and that's the same here. If we set lambda to 0, we have just our old least squares equation for finding the parameter estimates, and we have now changed this by inflating the covariance matrix here a little bit before taking the inverse. We inflated by the same amount in all dimensions. And that is the same as if we had been spreading out the data in all dimensions. So I'm again taking this example here of x1 and x2. And we had very little spread along the second dimension, and thus it became very hard for me to estimate the slope in this direction here. Whereas it was easy to estimate the slope in that direction because I have a lot of spread, my points support very well my estimate in that other dimension. And X transpose is a scatter matrix, and I'm now pretending to have more spread in each dimension that I really do. Now in the x1 dimension, this is going to change very little. So if I have, so I'm forgetting about, so I have zero correlation here, so I don't need the full matrix. So my variance in the first dimension, if I now add a little bit to it, if sigma 1 squared was already large, it's not going to change that value very much. But if on the other hand, if I change sigma 2 squared by the same amount, in relative terms, this is going to make a huge difference. If sigma 2 was very small initially. So by spreading out my observations, I bias the estimate of my slope towards smaller values. That makes sense qualitatively. Everybody happy? Okay, and I showed you in pictures that it actually works very well for this computed tomography example. Then I want to talk about a closely related method, namely principal component regression. Or PCR. What you do here is that you first project all of your observations to an R dimensional subspace. And then do an ordinary least squares calculation in that subspace. Now I would like you to explain to me in terms of this picture about spreading observations and so on, what this strategy amounts to. So if the data has zero correlation, like I've shown here, then that would be the first principal component. And that would be the second principal component. And now in this strategy here, what does it mean? Yeah, so we would then just have this dimension left, and we would just do a normal linear regression using this one feature. But another way of looking at this would be to say that I give infinite spread to the other dimensions. So if I now spread these data here to plus or minus infinity, that also means that my second regression coefficient beta 2 will have zero slope because the points are so far away now. So in that sense, it's even more extreme than ridge regression. It leaves, in this way of looking at it, it leaves the first dimensions alone and adds infinite amount of spread to the higher dimensions. So it leaves the dimensions 1 up to R, or the principal components 1 up to R alone, and it adds infinite spread to the other dimensions. And here in this picture I always used orthogonal features, but that's, the same argument holds if they're oriented in any way. So if they're oriented in this way, then that would be my first principal component, the one which I would leave untouched. And here if I take away the second principal component, it means I add an infinite amount of spread along that second dimension. Now, what's nice about these techniques is that they work pretty well, and both of them are extremely easy to implement. So principal components, you saw a few weeks ago that it's a two-liner or so in MATLAB, and ridge regression also, to solve this, so to add a little bit of a little bit of the identity matrix to your scatter matrix. That's also a very easy thing to do. Just as a comment, the actual way to solve this equation is not by really building the inverse, but you would rather solve the following. So you would, well, I'm writing this down explicitly. You solve for this using the backslash operator, which is if you're talking MATLAB, which is much cheaper than building the full matrix inverse. So solving a specific system of linear equations is cheaper than building the matrix inverse. So in MATLAB here you would write beta hat equals and then this equation and then backslash xy transpose. Okay, you have earned a break. So I forgot to show you the results from principal components regression. I've plotted the singular values and the reconstructions obtained with 2000, 1500 or 500 dimensions. And well, it looks like you need a pretty large number, 1,000 or so. Maybe even up to 1,500 of your principal components. So roughly you see here, this is where you still have information, and then this is where you have mainly noise after this shoulder. So both principal components regression and ridge regression they're easy to implement and they work pretty well in practice. But the solutions that all of these find are not sparse. Note I've left some place for the heading here, which will make its dramatic entrance a minute from now. Yeah, I should have said so before. The solution vectors are not sparse, and for example, in terms of principal components regression, you use few principal components, but these principal components typically involve all of the existing features. And if you want to have a simple model, so say one which depends on 3 or 4 variables only, or a model which requires only few features, this is not good. So to obtain sparsity, one would ideally want to solve the following problem, namely to minimize the sum of squares plus lambda times the L0 norm of beta, and the L0 norm of beta, this is the number of non-zero coefficients in this vector. Unfortunately, this is a combinatorial optimization problem. So you essentially have to try out all subsets to find the optimum solution to this problem, which is not feasible. And in 2004, Dave Donahoe showed that the Lasso, note the dramatic entrance, that the Lasso, whilst being a much simpler optimization problem, would actually with high probability find the correct coefficients. And the Lasso relaxes this constraint to the following. Again, sum of squares plus lambda times the L1 norm of beta. And if you look at the LP norms, so in general, what is an LP norm? So you take the pth square root of a sum over the coefficients taken to the power of p, and well, you know, let's say we take p of values of 0.5, of 1, of 2, of 3, and of infinity. Should probably have plotted this with computer, but for the L2 norm, the ISO contour for same distance, if these dimensions here are beta 1 and beta 2, the L2 norm is going to be a circle. The L3 norm is going to be like a square with rounded edges. So this is somehow interpolation between the circle and the square, which you obtain for the L infinity norm. Then there's the L1 norm, which looks like that. This is also called the Manhattan distance. And then you have norms for values smaller than 1, and they look roughly like this. Now note that for 1 and up, these areas are convex, whereas in the other direction they are not. And having a convex constraint set, and there is an equivalent constraint formulation for the Lasso, having a convex objective with a convex constraint set gives you a feasible problem, or one that's not too hard, whereas if you have a non-convex set such as this one here, it's much more expensive. And why is it not convex? For example, if you take this point and you connect them by a line, and this is lying outside the set. This is also called the Manhattan distance or city block distance, because if you live in New York and you have this grid of streets, then let's say to go from here to this point, or to go from here to that point, would be the same distance on foot. And if you look for all distances, also to this one would be the same distance. If you connect all these points that are of the same distance, then you end up with this trapezoidal structure. Okay, this is the Manhattan or city block distance. Okay, now there are two formulations of the Lasso. I've given you the energy formulation here. But there is an equivalent constraint formulation which says minimize the sum of squares such that the L1 norm of beta is less than or equal some constant. And you see this is a parabola, so this thing is convex, and that thing, this constraint, is convex. Or here we have a sum of two convex functions, which is also convex, and hence we have an optimization problem that has a single minimum. So what does this funny term do? We can look at it in terms of the energy formulation. So what's the effect of the regularization term? I can think of my residual sum of squares as a parabolic surface which has its minimum at my estimated value beta hat. And I'm now starting to manipulate this energy surface in the following way. So this is math and pictures. I've taken some parabola here, which is the red surface, and I've added a plane to it, the blue surface, and that gave me the new parabola, the green surface. And well, adding a linear term to a parabola still gives you a parabola, and one that's shifted in the direction of the negative gradient of your planar surface. So I could do this in one dimension by saying, you know, these y and x now, they have nothing to do with the regression. I'm just plotting a parabola here, and the formula for this would be, we have the curvature times x minus p, that's the position where it's located, plus some offset. So this would be the offset O, this would be the location P, and then the curvature would tell me how narrow it is. And if I'm now adding to this parabola, sorry, that's meant to be a lambda, this term lambda times the absolute value of x. So I'm adding to the parabola this. Then I have to distinguish two cases. So I could say this is cx squared minus 2x pc plus lambda x for x values larger than 0, or minus lambda x for x less than 0. And if I do this explicitly, I find that I have not changed my curvature, but I have changed the position. And this is necessary here to complete the square. And then something else shifted in the other direction for x less than 0. So in other words, the position of my parabola has shifted, and it has shifted by an amount that's linear in my parameter lambda. So what I get effectively is two different parabolas. One that has been shifted to the left, and another one that has been shifted to the right. And I'm now taking these here, splitting at position 0. So in the can we have the computer, please? So I should not have used kappa but lambda here. Let's say this is, to be consistent, I've shown you on the left hand the residual sum of squares as a function of the parameter that you use for a particular data set. I've fitted a linear regression to this particular data set, and the optimum parameter value is given by those parameters. So apparently we have, what was it? It was a an intercept of -2 and a slope of +1. You see, we have an intercept of -2 and a slope of +1. And our residual sum of squares is a quadratic surface around that point. It's a parabola, which you also see here. And you see that this parabola is not so well conditioned in the sense that we have a pretty strong constraint in this dimension here. But if I change slope and intercept in a correlated fashion as shown here, then my residual sum of squares will not grow very quickly. And I have now added to this error surface here more and more of a biasing term that you see here. So the biasing term is this absolute value of x. And, well, these are, in this case, 4 planes which meet at this point. And these planes always have, so the whole picture is continuous, also on these axes here. So I can now add more and more of this funny surface to my parabola. And in a way, by doing so, I obtain 4 different parabolas. You see, because I'm adding one plane here, so I'm trying to shift the center of the parabola towards that direction. Here I have a different shifted parabola, yet another different shifted parabola, and another parabola. But because this surface here is continuous, all of these parabolas also match up. So I have a discontinuity in the first derivative, but the function as a whole is still continuous, as you see here. Okay, so we have 4 parabolas that are somehow matched up in a funny way. And now there are 2 different ways of looking at it. In the energy formulation, I would simply say, okay, as I increase lambda, I track my optimum. And what I find is that by increasing lambda, my optimum will first shift in this direction and will then eventually go to 0, 0. And that's what's shown by the locations of these black marks. Or I could look at it in terms of the constraint formulation. I could look at it in terms of the constraint formulation. This is a little psychedelic. So here I've taken a different data set. This is why now my parabola is in a different position, oriented in a different way. But I've taken this data set, and again, in red you see the residual sum of squares. This would be the optimum parameter values. So the x's are beta 1 and beta 2. This would be my optimum estimate according to least squares. And in the constraint formulation, I'm now looking for the lowest value of this red function. And these are isocontour lines, so here's the minimum, and from there on it grows. I'm looking for the smallest value subject to the L1 norm being smaller than some value. And the L1 norm isocontours are shown by these black lines. So this would be a short L1 distance, this would be a somewhat longer L1 distance, and so on. So let's say our unconstrained solution is here. And if I now constrain it to the next shortest L1 distance, I would get this solution. And then I would get that solution, and so on. Nothing exciting happening until this point where one of my 2 regression coefficients has become 0. So now I still have this value for beta 2, but beta 1 has disappeared, right? Because our coordinate system is centered here. So at this point, I've gone from a linear model involving 2 explanatory variables to a linear model involving just a single variable. And now we start to constrain it further. So I'm now looking for the lowest energy solution within this rectangle, which happens to be here, and then within that trapezoid, which happens to be there, and so on. Until I'm, at the solution where I say, okay, both coefficients are 0 and everything you saw was just noise. So we followed, it turns out that we followed a linear path here, and yet another linear path there. And this is exploited numerically by an algorithm called LARS, which follows this path in the opposite direction. Does that make sense? No. Wild laughter. Okay. Try and ask questions, please.
I think you just constructed it in a way that you go to the corner. I don't see why it should be that case in general. So what if the ellipsoid is orthogonal on the rhomboid? Then the minimum is on an isocontour and not in a corner, for example. Or is it?
If it's rotated which way? I didn't understand. If it's rotated which way?
Orthogonal, slightly. Wait a second.
Why do we want to minimize the distance with respect to the norm? I mean, in this particular case, we saw that the estimated values were greater than the real values, but I mean, this won't happen in general, will it?
So what will happen in general is that for coefficients that should be 0, if you add noise, then you will find values larger than 0. So there is an interest in making these smaller. Unfortunately, you're also making your coefficients, which should be non-zero, you're also making them a little bit smaller. However, they will typically offer more resistance to the shrinkage, and that has to do with how this is oriented. And how this is oriented is a consequence of how your data is distributed. Because the shape of this thing here, the shape of this ellipsis was dictated by x transpose to the -1, because this was the covariance matrix of my parameter estimates if I multiplied with sigma squared. And now I'm trying to understand the other question again. You say I constructed this by making, or it should be orthogonal in which way?
If one of the main axes of the ellipsoid points to the origin,
Yes.
then
Then I shrink both at the same time.
always cross in the middle and never in the corner.
Okay. Okay. So if the long axis of this is directly pointing towards my coordinate system, and now these are here the constraints that I'm plotting, then you would shrink two variables simultaneously. That is correct, so they would both go to 0 at the same rate. It's just not very likely. So if you can orient your ellipsoid in in an arbitrary fashion, it's not very likely that you're exactly going to hit.
I'd say if it's a little bit
Tilted, yeah,
you
you will.
hitting the corner almost at the origin.
Yes,
Most of the time you pass
yes, that's correct.
the limit, so it's not sparse.
but towards the end it will be. Yes, I agree. I agree.
So the goal of this whole thing is to reduce noise?
In your parameter estimates, yes. So you artificially modify your parameter estimate so as to make them more robust to noise. Yes, that's correct. Is it what? The only? Yes. We want to get a parameter estimate which is stable in the face of collinearities. Oh, we don't need a computer. Okay, so let me try and draw a different picture. I am still hoping to convince you that this is not, or so why do these things induce sparsity? I'm here using an argument by Bach and colleagues. Let's assume for the moment that our residual sum of squares potential is isotropic, which normally it isn't, but I have to make some choice now. And let's say that this is the origin of my coordinate system. So where will it, if I now constrain this to smaller values of my, so these are the constrained isocontours that I could use. So for example, if I'm constraining to this particular distance here, I would have, so this was beta hat. If I'm constraining to this particular distance, I would have shrunk both coefficients. However, if I am now, this is hard. If I'm now constraining it to, I need to go further. Probably at this point here. So I'm looking for the point where the tangents are aligned. At this point here, one of the coefficients has become 0. Okay, so I've shrunk along this path. And at this point, in a linear fashion, by the way, and at this point, one of the coefficients have become 0. Now, if I'm asking where, in what region this would have happened, that eventually one of the coefficients is going to hit 0, I can ask the other way around. I can ask for, if I'm now fixing this distance here, so I'm saying I'm looking for solutions that have an L1 norm that is indicated by this trapezoid here, which is the set of beta hats that would map to this corner here. And the answer is that if I use an isotropic, or if I assume an isotropic residual sum of squares function, then everything in this entire region here, in this half space, would map to this point, or it would eventually reach this point. And similarly for the other corners. So if a coefficient vector This is beta 1. This is beta 2. And if a coefficient vector that I estimate, beta hat, lies, say, here, and if I'm assuming isotropy, then my lowest energy point will be here. And this is true for all coefficient vectors that were lying in this area here. Whereas coefficient vectors in this half space will first touch this line and so on. Yes?
Why did you follow the line as you did it up on the sketch? When you go for the intersection points between the norm and the
Constraint set?
lines of the Gaussian?
Why did I draw a linear line here? Was that your question?
Because when you go for the intersection points between the L2 norm and the Gaussian lines.
Okay. So I am always looking for that point where the Gaussian has the smallest height, or the parabola has the lowest height for a given L1 distance. So this would be, this point that I showed here would be for this particular L1 norm here.
Oh, you're not looking at the same distances as in the Theorem.
I here plotted the points on the isocontour lines. Oh, okay. I'm not sure I'm making a good job of this. So,
If you have given a distance,
yeah,
you drew them in a certain pattern, and let's say it's
okay.
the ones you want to look at, then wouldn't you go for the, if it's a given line, wouldn't you go for the intersection point?
Not the intersection, no. I'm looking for a place where the tangents are aligned.
Which tangents?
Of my parabola and of my constraint. Let's say I'm taking a new sheet of paper. So let's say here is my parabola, and these are my constraint terms. Now the lowest point of the parabola within this constraint lies here, because there are more isocontour lines that I did not draw. Okay, so there were more contour lines here, and at this point here they were exactly tangential. Yeah.
And what kind of tangents are you talking about?
Oh, the tangent between the so I want the isocontour of the parabola to touch the isocontour of the constraint line. Yeah. Okay, so back to this picture. Can you see why all of these regions of feature space map to this single corner? So I argue that this entire region here of parameter space is mapped to this corner when I start to shrink. And this entire part of parameter space is mapped to that corner, and so on. Okay, there's somebody who sees it. Great. And we can go on. No. So the argument was that if I have a parameter that lies, for example, somewhere here in this red region, and if I now require that it must lie, I'm looking for a solution within this feasible region here, then if I have a parabola around my parameter, then the first point where it will hit my constraint line is this point here. So, in other words, the singularities on my constraint set they account for much of parameter space. So the red point here is just a single dot on my entire constraint set, and yet it accumulates this much of parameter space. And this is why one is trying to construct constraint sets that have singularities. Okay, now I don't have the time to show that actually the solution path is linear, and I don't even have time to write down the LARS algorithm. So what the LARS algorithm does is it starts at 0, and it then asks which of my features has the strongest correlation with the response vector. And then it starts including some of this feature until we get to a point where we should include another explanatory variable. And which is this point? It is the point where the correlation between any of my non-selected features with the response becomes as large as the correlation between the residual of my current regression using only a subset. And at this point you start to include a second variable and so on. In other words, you get a piecewise linear solution path using the LARS algorithm that starts at 0 and that ends at the ordinary least square solution. And it is now a matter of choosing this regularization parameter well. And this LARS, by the way, is just a computational trick. You could otherwise solve this as a quadratic programming problem, but it's cheaper if you use this special algorithm that I just mentioned.